good to see you. And well, we're very happy to have a very distinguished speaker today. It's Professor Bai from the Department of Computer Science at UC Davis, and he's a distinguished professor at that department. Professor Bai obtained his PhD from Fudan University in China, and he did a postdoc at Courant Institute, New York, and he's a SIME fellow and co-developer of the software package LayPack. I hope I pronounced that correctly. It's a linear, I'm pretty sure it's a numerical linear algebra software package. And that's, I think, what this talk is going to be about, numerical linear algebra, or as one of my postdoc mentors called it, the key to the kingdom. Okay, the stage is yours, Professor Bai.
All right, thank you all. So really, first of all, really appreciate the host of Zhaojun and the team and Simone invited me and give me this opportunity to meet all of you. It's a virtual world, but nevertheless, it's still feel very closely when you actually see a small group of people and talk about something of has some mutual common interests and something. So it's very appreciate the opportunity of speaking to you and to give a seminar. So my talk will be on the two keywords I called. One is called Rayleigh quotient optimization, and the other is called eigenvalue problems. So
Professor Bai, do you want to share your slides?
Yes. So probably, as you probably will naturally ask, what those two, what are you going to talk about under this? So this is what I'm going to say. Okay. So first, I want to start it with an acknowledgement. So this is has been a subject I have been pursued in the last, if it's not 10 years, at least 7, 8 years. So I started within people in mathematics and also collaborated in chemistry, physics. And these days, of course, you also are working with people primarily through some of my former students. And now they work for Microsoft, LinkedIn, or Expedia AI group, etc. So those are a group of people I have been collaborating on this projects, and also has been supported by the National Science Foundations from the Department of Mathematical Sciences, Division of Mathematical Sciences, and also computing and also material science. So you will see why this subject I'm going to talk about intact with all those different groups. So here is the so-called Rayleigh quotient. So primarily, I also apologize to those advanced listeners in advance, in the sense of quite a part of my lecture, I tried to be very tutorial, introductory for those of the students who are interested in such subject. Also, they wanted to learn the close connection between the textbook material they learned and to the so-called publishable results, or you can publish paper, say, in a science journal, and how to, what's the gap and what you're talking about. Okay, so this is a lot of introductory material of that. So we started using this quantity, so-called Rayleigh quotient. So namely is that you are given the two matrices, A and B. So two symmetric matrices, and also for simplicity, assume B is positive definitely. And then you can define this ratio of bilinear form. So this quantity in a slightly simplified form has been proposed as early as 1870s. So when Rayleigh, he's prominently of at that time's mathematics, and mechanics engineering. So if you're looking at this book called A Theory of the Sound, basically started this so-called acoustic of fields, sound and waves, those study in this book published in 1877, and this quantity is already used extensively to discuss the vibrations and the sound transition, etc. So another amazing is about this particular books is that the first edition published in 1877, but it has been published multiple times, even up to today. You still can order this book online, and so far, and it's called A Sound of Theory. There's 2 volumes, etc. It's still pretty much modern context in the sense of study of that. So for this particular this is the history of the little bit history of this quantity. So if you are interested, of course, you can find more on that. So regarding this particular of this quantity, so people are typically interested in the following optimization problems. Either you try to find a minimum maximum of this quantity, or you restrict it to certain space, and then you try to find a min max of that. So finally, you're also probably interested in a set of the project you might call a projection on a certain space, and then you are interested in the trace of that quantity as subjected to that. So those are we call the classical Rayleigh quotient optimization problems. It's called a classical, and also means that you can literally find almost in any textbooks on advanced numerical linear algebra or matrix theory. So now if you take a pause for those graduate students, so you can ask yourself, well, how much do you know about, or you have learned about those quantity optimization problems listed here. So here it's an important of results. It's called a variational principle. What it says that if you're looking at the eigenvalues of this matrix pair, just our definition of AX equal to lambda BX. If you put all the eigenvalue ordered from small to large, then here is the answer to all those optimization problems. The minimum ones of Rayleigh quotient is corresponding to smallest eigenvalue. Maximum one is largest eigenvalue. And so the min max of if you're looking at a subspace of dimension J and the corresponding to J's eigenvalue. And finally, the trace of this is corresponding to the sum of the first K, if you're looking at a subspace of the matrix's size of M by K. So those things is formulated the foundation of that. So as listed here, it's a very classical and has a lot of more extended version, etc. Those are very well studied, and also sort of almost you have to learn this in every optimization numerical linear algebra courses, and also in matrix theory. So in other words, within this variational principle, so immediately you see that if you think about Rayleigh quotient optimization problems, it's turning into an eigenvalue problem. The eigenvalue problems, it's a very classical problems in linear algebra. There's lots of efficient linear algebra solvers. So therefore, those eigenvalue problems can be turned into, those optimization problems turned into an eigenvalue problems. So vice versa. So opposite of that, you think about it. If I have an eigenvalue problems, AX equal to lambda BX, okay? So now I can, using those variational principle, I know it's corresponding to Rayleigh quotient optimization. But we also know there is a huge of nice tools and the techniques in optimization. In other words, most prominently or simple entrance level of algorithm like a conjugated gradient method, and now you can use them to solve an eigenvalue problems. So those are the really build a beautiful connection between these two of you might call the subject. So here it's a simple example. It's a very cute, and every student can play around very easily. So as you know, the graph is a very basic model, mathematical model. So a graph is simply consists of a set of we call the nodes or vertex, and also the edges, which talk about the connectivity between the vertex. So now let's assume you want to draw this graph. What this meaning is that you want to find a mapping from this vertex and mapping them to our familiar the Euclidean space. For example, if you draw it on a piece of papers, is R2, or if you draw it then on a 3-dimensional is R3. So therefore, you want to find such a mapping to mapping each vertex to a vertex of in this Euclidean space of Rm. So if you're looking at this, so what will be a nice draw or a very you might call it nature of a graph, because when you draw the graph, you probably just randomly put down some nodes and then follow the edge. But now you want to form certain of a more naturally looking or very reviewing the structure of underlying graph, etc. So you can basically looking for this omega function transformation functions here, or in a matrix term, you're looking for the matrix is R, because every vertex now mapping to a vector in the Rm. So when we use optimal R, you can think is that I can define the so-called energy of this drawing, which is just making the difference between each of the vector in this Rm space. So what you do is that you want to draw this in a way to with least tension, you might call it, or extended, the stress, you might call it. If you think about all the spring connecting all those vertex, if they are connected, and then you try to find the so-called define energy, and then you try to minimizing this energy. It turned out that this quantity you want to minimizing, in other words, is the energies that people call it, and it's equivalent to trace of this quantity here. And this L matrices here is just the so-called Laplacian of matrices. It's coming from the adjacency and plus the degree, minus the degrees of these matrices. So therefore, this is a way of that. So now let's, within this concept, so now let's see how I'm following this to do if you give me some graph, and how can I draw it then in a nature and a nice way. So as you can see, fundamentally, is you need to solving this eigenvalue problems, is right? Because this trace is just going to be some of the smallest eigenvalues of L, this Laplacian matrices. So here it's a simple example. For example, when you given a matrices, given a graph, and we typically using so-called adjacency matrix. And here is the adjacency matrix of the 60. It's a graph with 60 nodes. So you're looking at this graph and it tell you what's how the vertex adjacent to each other. If you draw it then on piece of paper, you probably lost the tracking of all this, or what's the more natural way underneath of that. On the other hand, if you follow the one we suggested earlier, so you formulate a Laplacian matrix L here, and then you compute, because this is corresponding to the eigenvalue, the R is corresponding to the eigenvector of second and third smallest. So therefore, if you compute its eigenvalues and eigenvector of this Laplacian matrix, and then you use second and third eigenvector, because the first eigenvector is naturally of all the ones, is the trivial ones. If you draw it then in the second and the third, and you plot this, so bingo. So you got a very nice natural representation of that. So in other words, this graph, and from the left-hand side of these matrices, does not reveal you really nice structure of this topology or nature of this graph. But at the right of this really tell you this is an interested of a bucketball structure. So there's a lot of such work done. For example, I give you two references. One is that it's a very beautiful survey article and talk about how to draw the graphs using the eigenvectors and through this minimization I talked about earlier. And also many of us do matrix computation. We're using this site to do the matrix, to go there to accessing these matrices for test the different type of your algorithms. And over there, you might find on this website, there's a lot, it's a very colorful website. It's not like matrices itself, it looks very boring. So therefore, you might be wondering, how they do such all these sparse matrices to draw this pretty picture. Of course, there's other techniques too, but this one of that is the key is through this really quotient optimization. Okay, so this is my 10 minutes introduction. So now for the rest of that talks, so I will split into the parts. I will give you a very quick review on the work beyond those classical really quotient optimization or the eigenvalue problems you saw earlier. And then I will give two examples, which is more connected to the more recent work. And because of this type of problems, it's coming from the traditional computational science and engineering, we call it, such as computational chemistry or computational physics. So I will using that example first, linear response eigenvalue as an example to illustrating the connection between the really quotient optimization and the eigenvalue problems. The second one is more the more recent work. It's on the you might call it imaging segmentation or data clustering or graph partitioning, etc. Okay, so then I make a brief conclusion remarks.
Professor Bai, one question was asked in the chat about the drawing functions W or omega. What are the assumptions on these functions?
There's no, as I say, it's just a transformation of vertex to a vector. You can define of that, but for now, for us, we just define a plan order once, the nodes.
Okay.
Yeah.
Thanks.
Yeah, it's good. Of course, you define the different functions and also define the distance different way. It's going to be leads to different types of that. In fact, I'm going to mention a very recent work on that. Okay, so here it's so let's looking at beyond the classical really quotient optimization. Okay, so as you can see, this is a very basic. So what's the people has done since the in the last of whatever a year you're talking about. So let's start it again using a very simple-minded example. So you studied, we all know that as so-called dimension reduction is a very fundamental tool to deal with high dimensional data. So what that meaning is that if you want to do any type of analysis, of course, the most well-known is the so-called principal components analysis. So you can imagine you are given a data, let's say X1 vector, and all this is living in a very higher dimensional space of D. Okay, so in other words, X is X1, X2, etc. You can just imagine it's the pictures of photos you want to analysis on that. So of course, they are all very higher resolution, higher pixel numbers, and leads to a higher of D. So in this case, what you do is the so-called dimensional reduction techniques. Essentially, is you define appropriate objective functions, and then you're looking at vector of the matrices of bunch of vector, and then to subject to optimizing certain type of objective function, and then afterwards, once you find the design of the projector matrices P, and then you can mapping this all your data set onto that subspace, okay? Onto, not a subspace, so making that a transformation, now your Y will be lived in a subspace is of a dimension much smaller than the original of that. So this is basically the one line description of what's called a linear dimensional reduction. So simply is just like this. For example, all those dots here across here, red or blue, are living the 2D. And then if you find a 1D line, so now you are mapping all this 2D data onto that 1D. As you can see, if you find these lines, and there's a natural clustering of original data, it's already also can be reflected on this 1D on the lower dimensional space. So one of the widely using the techniques called a linear discriminant analysis. LDA is a Fisher's linear discriminant analysis. So what they do is that they're looking at the P, or we're using the space of V transpose. It's namely is trying to maximizing this objective function F here. So in other words, it's a trace ratio of that. In other words, roughly is just to say, once you have a data, you can define is called a covariance between the and within the cluster and between the classes. And then what you wanted to do is that you wanted to maximizing the difference between the classes and minimizing of the difference within the cluster. So this is basically the LDA formulation of that. So as you can see, this is not the standard class, the trace ratio optimization problem, trace problems, because you added a ratio up here, okay? So in other words, you're naturally asking, so what's the, how to solve this problems, this ratio optimization problems? So one case is say, if you are mapping to a line, so in other words, the dimension of this V here is just a vector. So as immediately you see, this is just Rayleigh quotient optimization problems. So yeah, this V is just the top eigenvectors of this, meaning for this matrices, the eigenvector corresponding to the largest eigenvalues. So if you do this, then you will get the this I showed you earlier. So again, this is of the data set, and then you define it, and then afterwards you project on a 1D. That's what you got. So in the reality, in the past, people deal with higher dimensional because you want to project it to more than 1D. So what they do is that they still just using this top, the so-called R eigenvectors anyway. Although in this case, you need to asking yourself whether this is a V of here, optimum V is corresponding to the top eigenvector or not. So, but nevertheless, people just using them, we call it heuristically. But then, as you can see, the results could be very suboptimal. So in fact, in this data set here, there's 3 clusters. Now you want to mapping them on the 2D space. As you can see, they're completely tangled, and you cannot separate it. So back to, started quite a while ago, it's about 10 years ago, but later graduate settled. It turned out is that this Rayleigh quotient optimization problems you saw earlier, okay? So this is, again, this eigenvalue, this optimization problems of here, the trace ratio of that. In fact, it's not corresponding to a linear eigenvalue problems. It's corresponding to a nonlinear eigenvector, nonlinear eigenvalue problems. Furthermore, the nonlinearity is with respect to the eigenvector. What this meaning is that the optimum solution for that eigenvalue is equivalent to the eigenvalue problems of this. So in particular here, the coefficiency matrix V here at the H here is dependent on the eigenvector you are looking for. So this is what we call a nonlinear eigenvector, a nonlinear eigenvalue problems with respect to eigenvector nonlinearity, or sometimes people today is called a nonlinear eigenvector problems. So for short, I will just use the MEPV to stand to such eigenvalue problems. So it turned out you need to equivalent to solve this. Of course, the question is how can you solve this? And it turned out is that the simple techniques and also most effective way to do this is by using the so-called self-consistent field iteration, because you can start it with the initial of V, and then you turn this matrices to be you might call it constant matrices, and then you solve this recursively. And further, for these problems, is you can nicely to prove it will be globally convergent, and also the local convergence rate is quadratic. In other words, computationally is also very efficient. So similar.
Can I ask a question?
Yes.
Just about the optimization problem 1.
Yes.
So is it clear that that has a unique global maximizer?
If the sigma b is positive, definitely, yes.
Okay, but can you go to the optimization problem again?
Yeah, this.
But that's not, I mean, that's not a convex problem, right? Because V transpose V is not a I don't know, I don't even know about the objective function. There might be something, but V transpose V is the identity, certainly not a convex constraint, right?
Yes. But for this problem, it's proved that there is existing a global optimizer.
Okay.
Yeah.
And it's unique?
That's a good question. I probably will hold on to answer you this.
Oh, sure, because you have this local convergence result. That doesn't mean that there's something globally going on. But I was also wondering where the quadratic rate comes from. Is there any type of Newton iteration that, like this linear iteration?
It's to show you the SCF eventually will be quadratically converging.
Yeah, because this SCF iteration, I mean, I'm not saying it's a Newton iteration, but it looks suspicious. But okay.
Yeah. Okay, so thank you for watching.
But if you have a global convergence result and you start from another solution, wouldn't you stay there? So if there is a global convergence result, doesn't that mean that there is a unique solution?
Like I say, I need to check the global solution, whether it's unique or not. So this is the results published by this group of people in about 10 years ago. But more recently is the group of people who, including me and my students, working on some local convergence rate. Okay. All right. So here is the trade-off or the main pictures of that. So in this picture, as I showed you earlier, so there is a 3 cluster. So for this optimization problems, as you can see, it can be considered an optimization on the Stifel manifold. So therefore, there is a so-called Stifel manifold trust region type of method. And if some of you using this man-ops toolbox, you know you can solve that problems using this optimization problems on the manifold. So this is the solution. You can see that basically preserve the nature of the original 3 cluster on the 3D space mapping to the 2D. But also this using this nonlinear eigenvalue problems, eigenvector solver, as you can see, we almost get the same results. Okay, but the message is that if you use the optimization tool, the cost grows rapidly within the dimension of increase. But if using a linear eigenvalue solver, it's the results is bad, but the cost is very effective. So it's almost flat. But now using this new solver, using a nonlinear eigenvector solver, so our cost will be just slightly more than just of linear eigenvalue solver. So in other words, you get the optimal solutions as you would like. So therefore, so here it's so this is regarding this work. As I said earlier, the measurement of here is using a traditional trace ratio, but you could involve more complicated of this distance metric, etc. So just published last year, at the end of the last year, there is new papers and working on the so-called using the optimal transport distance and to do the Fisher LDA, and then leads to similar and nonlinear eigenvector problems as I described here. It's slightly, of course, more complicated, but the essence are similar. For those of you, if you want to interested, you can look at the latest publication on the NIPS. Okay, so within this, so let's move on. In a sense of there is over the last many decades, there's an enormous synergistic effort to generalize those classical Rayleigh quotient to more today we call a Rayleigh quotient types of the model, and to review the various different principles and also underline the eigenvalue problems and vice versa. So here it's one direction. I give you quick references. So many of those started with Rayleigh quotient or Rayleigh types of Rayleigh quotient and review its variational principle and ultimately lead to solve the eigenvalue problems. And you can think about it, you not only necessarily the matrices in earlier I talk about it is a symmetric, definitely pencil, meaning B has to be positive, definitely. But now you can extending them to more general class of the matrices. And also you can put some various constraint on the Rayleigh quotients. And the trace ratio you already see briefly earlier. And there's more general version is you have a sum of a trace of such ratios. And finally, you can also do, we call it robust, meaning the matrices over here, A and B are constants matrix, but in the reality, the elements of those matrices is subject to certain uncertainty. Okay, so you're assuming those matrices, the variables, are restricted to certain domain or use certain bound, etc. And you can incorporate that into this. And finally, you can also impose certain orthogonality condition, like in this orthogonal canonic correlation CCA analysis. So all this work, particularly as you can see, some of them are very recently published. So that's one direction. The other direction is that also people started with eigenvalue problems, and then from those eigenvalue problems, they review what's the underlying of the variational principle, or particularly in this case, the Rayleigh quotient types of that, and then build the Rayleigh variational principle. Of course, once you have that, and then you can use the so-called the optimization techniques to solve those eigenvalue problems. And here I listed 4 types of work, particular more latest, like last one, there is a very nice long survey articles published by Hans Voss from Germany, etc., and with his students. And even for nonlinear eigenvalue problems of these types, and under the certain assumptions on those nonlinearity, there is also corresponding such kind of variational principles and so on. So therefore, within those both theoretical results, as you can see, are primarily variational principle, but those leads to lots of the interesting algorithm development and also applications. And so, for example, in electronic structure calculation in material science, and also today, a lot of us are working on data science or data analysis, you will find that there is a wide application into both. So for the rest of this, I will quickly, within the time I will try to finish by 5 p.m. sharp. Okay, so within roughly 20 minutes. So I'm going to go through 2 examples to illustrating of this 2-way of directions work, two direction work. One is I first started within this so-called linear response eigenvalue problems. So in this case, we started with an eigenvalue problems. You might call it, there's even no hint. There should have some Rayleigh quotient type of characterization, and not even think about it. For those type of problem, you will have variational principle. But surprisingly, the answer is yes. So this is a so-called linear response eigenvalue problems. You are given the 2 matrices, A, B, both are symmetric. For my presentations, I also assuming this symmetric version, if you put A, B, B, A is a positive definitely matrices, okay? So this restriction can be weakened. But nevertheless, for now, let's just us making this assumption. Then you need to consider this so-called non-symmetric eigenvalue problems, because you need to compute eigenvalues and eigenvector of A, B, minus B, minus A. Okay, as you can see instantly, this is a non-symmetric eigenvalue problems. So in other words, in the references, people call this it's a linear response eigenvalue problem. It's non-symmetric. So as one way you can writing down this is just simply you make a little transformation because you have A, B minus A. If you're doing a simple orthogonal transformation, you let's A minus B, A plus B, you define the two new matrices. So in fact, this eigenvalue province can be simply transformed this, you call the anti-diagonal eigenvalue province. So two of them are coupled, twist of that together, okay? So it meaning Kx equal to lambda y and My equal to lambda x. So this is a coupled of that. So this is the, for this type of eigenvalue province, it's very widely studied. As early as even references back to, as I show you here, is the earlier 60s. And then the people study this up to today, a lot of study, and but depend on the field, and some people call it linear response because it's talk about the first order of approximation to a highly nonlinear system. The other people also call the Bessel-Salpeter's eigenvalue province, because this is for modern terms, which is quite popular in so-called excitation states calculation. So if you talk with people in computational chemistry or physics, they do material science, this is a very well-known types of the eigenvalue province. So now, naturally, we are interested in eigenvalue, particularly those eigenvalue which has a positive and a negative. So what interested is that you're interested in the smallest positive eigenvalue, which is people in physics called first excited states. So in this case, and then in 1961, so this physicist David Solis, okay, so he won the Nobel Prize in 2016 for topological insulate of this work. And he showed that the smallest positive eigenvalue of this matrices can be characterizing of minimizing this functional. So this functional is in his original definition is in this way. In other words, he making the numerator matrix to be symmetric and put a negative in a denominator. Of course, in this case, this is, you might find it's a very, of course, we're assuming they are not equal to 0, etc. Avoid all that. So if writing down equivalently in this Km matrix I showed you earlier, it's just can be written in this way. In other words, this eigenvalue province having a such a so-called minimization principle. So Solis in his original paper made this discovery through the physics argument. It's quite amazing. But rigorously mathematical proved is actually not very hard in a sense, but people really pay attention in using that for a long time. But it was not rigorously proved that until 1990s. But when we, about 7, 8 years or 9, 10 years now, whatever you're counting, to encounter this, so we are naturally first interested is in the physics or chemistry calculation, people are not only interested in the smallest eigenvalue, they're also interested in a bunch of a set of smallest eigenvalue. So in other words, naturally you ask from this form, is that corresponding the trace, or you might call the subspace characterization or organization? It turned out yes. So you can have a very nicely subspace version of this. In other words, if you define a trace in this way, and then you can subject it to this minimization, okay, subject to this bi-orthogonality constraint, and then you can prove indeed this is corresponding to the sum of the k smallest positive eigenvalue. So this results itself are quite in a sense of a very clear generalization of what's original node, and also very inspired in algorithm design, because once you have this, then you know that your optimum now is how to design an optimization method to solve this problems. So we first prove, and using this results back to now, it's almost 10 years ago, we did a bunch of that related work. So within this, so for algorithm, we instantly, as you can see now, I can design an optimization method. I can use a conjugated gradient type of method to optimizing these problems and so on. So here is some technical details from the conjugated gradient and translated to the, how to do the line search and etc. So this is the techniques that can be instantly developed. And all this is not very surprising in terms of itself, the development, but nevertheless, the efficiency is quite amazing. So let me just jumping around. For example, using such optimization techniques now, we can solve of such eigenvalue using the various different techniques. Here we are using the extended conjugated gradient method. It's called a locally optimal block conjugated gradient. Now you also can do so-called preconditioning, subspace extension. For this particular examples, we can reduce from the original trivial version of a conjugated gradient from the iteration number of 600 subspace to 250 iterations, and further reduce down to only 50 iterations. So the key is this picture is show you, if you are interested in a certain number, in this case, the 10 smallest eigenvalue, but you can set your subspace dimension is 4. So in other words, every time you keep tracking 4 smallest eigenvalue, once one of them is converging, then you deflating those converging to one and then introduce a new one until all the 10 eigenvalue you wanted being computed. So such as, in other words, it's turned out it's why we want to do this. The reason is this type of problems, dimension grows very rapidly. So for such a simple molecule structure, the dimension is already added to 2 millions. But if you want to do a realistically of that, like a C60 of a fluorines of C60, so dimension is already 22 millions. So really you have to maintain the so-called memory consumption for such a type of that. So conjugated gradient type of method is particularly efficient for that. So in other words, you transform such eigenvalue problems to a optimization through this variational characterization. Then you can use the lower memory cost type of conjugated gradient method to solve this. Even on this is all done in a regular workstation. So you don't need to using the so-called supercomputer to do such calculations of that. So for the rest of the about 10 minutes, so I'm going to show you another direction, which is started within the Rayleigh quotient or Rayleigh type of models of problems. And then we uncover what's the variational principles, meaning connecting with eigenvalue problems. And then we can solve this eigenvalue problems. In a certain sense, this is just extending to the earlier of choice ratio optimization problems that you have seen, okay? So I'm using this very accessible of the example. By the way, for all these 2 examples you saw here, or 2 of these things, if you visit my website, looking at the of this, you can accessing not only the publication on this, you can also accessing the so-called website, which provide all the code, the MATLAB code to reproduce of those plots. And for particular for those of students who are interested to get involved into such research, and you can have some head started on that. So here is a very generic or very simple problems. It's so-called graph partitioning. People also call it imaging segmentation. So you have an imaging like this. So there is a flower daisy in the center of that pictures. So what you like to do is you want to cut off this, or you want to extracting that feature from this graph. So this is what you wanted to get. So the way of you doing that using the Grafton graph partitioning is you given a graph, and here the edge we use weight, meaning how many different pixels, how much they are strongly connected. Then what you want to do is you want to take a part of that out. We call it a cut. It's basically just a subset of the vertex. And then you can define this cut value, essentially just counting the weights or you removed between this of the original and this subset. And then you can also define the volume, namely is how heavy and this subcluster itself. So the partitioning province, namely, is that you want to have a partition of all those vertex, and they are virtually of an disjoint. And the key is the third one. So it's not, you can debating how to precisely define that. Namely is that you want to, between the cluster, you want a connection to be low, it has lower weights, but within the cluster, you want to have high weights. So this is basically of that. Of course, the most simple case is just a binary. And in most cases, you see when we study this or work on this, we study with k equal to 2. So there is a lot of way to define this so-called cuts. Okay, there's a min-max cut and so on, max cut, etc. So here it's a technique that is studied now, is looking back almost 20 years ago. It's called a normalized cut. Namely, it's a balanced cut value within the volume between the both of, two sets. You think about this is just binary cuts, okay? So define this. So they want to try to balancing it. Then afterwards, you define an indicating vector for each of vertex. Depending on whether he's in cut or not in a cut, you use the two binary variable to representing this. So again, those 2 minus 2b is just artificial because later for expression easy. So afterwards, you can show this normalized cut can be represented as a ratio, trace ratios, as a Rayleigh quotient, sorry, it's not trace ratio. Okay, so it's just the Rayleigh quotients of that and subject to this constraint. So therefore, the way of doing that, you want to minimizing this, we call a minimum cut. In other words, of that leads to such a binary optimization province. So of course, this binary optimization province is, we all know, is hard to solve. So what you do is that you do the relaxation. So instead of find a binary value, you just say, I find a real vector on this IM space. And then I just decide of that. So once you solve this eigenvalue problem, the Rayleigh quotient optimization province, and instantly you know this is corresponding to the second smallest eigenvalues of this. So therefore, essentially this minimum normalized cut and turn in the end, turn into this eigenvalue province. So notice that this eigenvalue province, the coefficient, the Laplacian matrix here typically is extremely large, and also positive, the matrix that we are assuming this original data is connected, so it's a diagonal matrix is positive. And also in the reality for such vector you are looking for is really very low dimension. So therefore, that you can use a lot of the eigenvalue solvers such as a conjugated gradient method. I mentioned that earlier, and to do such calculation, this is people doing that. So of course, if you want to do multiple cut, what they do is that you're just computing this matrices, the k, if you're assuming you want a k smallest cluster instead of 2, you're just computing k smallest eigenvalues corresponding to eigenvector. And then you use those eigenvector to do the clustering. Okay, so this is same synergy as I showed you earlier. So here it's a very simple example. For example, you have a data looks like this. And then if you're computing this matrices using their nature, the Euclidean distance as a measure, so you compute its eigenvector. This first eigenvector, of course, we know is a constant. And this is second eigenvector. You're looking at each of the components. And this is third eigenvector, and this is the fourth eigenvector. So of course, if you use the eigenvector to do binary cut, using this eigenvector to do binary cut, so this will suggest that these two will be in one cluster and this another cluster. So if you do the 4-way cut using this fourth eigenvectors, you do the clustering. So it's naturally tell you those are the 4 clusters of the data. So in other words, it works quite amazingly good. But of course, in the reality, it's always tough. So for example, if you have imaging like this, and then if you do that standard of two-way cut, so the segmentation will look like this. In other words, very disappointing instead of extracting this camel of this on this. So what's the people to resolve that? What they do is that, and also increasingly you see people getting into that is in the sense of they insert a certain domain knowledge. So what this domain knowledge is meaning that they put a certain constraint on this Rayleigh quotient. So in this case, they just provide a few points, a few pixels, say all these blue dots has to be in one cluster. All those green dots has to be in another cluster. So therefore they say, basically you have so-called in-cluster or must link information and cannot link information. You just provide a few of this, like in this picture you saw here, this has hundreds of thousands of pixels. You just provide a few of dots, but afterwards within those information, you can get a very, very decent cuts. Okay, so this is another name is so-called constrained spectrum clustering. So within this, essentially, as I say, you do the original clustering, but now you are provided so-called must link and cannot link structure. So in this case now, there's various techniques and to embedding this must link and cannot link. In one way, people call a soft link, a soft constraint, meaning try to put those constraints into the original Laplacian matrix. So in this case now, you encounter a matrix pencil, which is a singular pencil, has a common norm space. This is beyond what the traditional Rayleigh quotient can handle. So therefore, you must addressing how to do this. So this is one work we have done a couple of years ago. But more recently, we find you can also do so-called hard constraint. In other words, you put those dot point explicitly into your constraint. In other words, within this, now nicely, this can be reformulated into a traditional Rayleigh quotient, but now within of a linear constraint, because this is the linear constraint of sets, is right. So it's just because those C embedded all this constrained information you wanted to do this. But it turned out this is a very well studied province in our numerical linear algebra community. But this constrained eigenvalue province is turned out equivalent to a quadratic eigenvalue province, because in this case now you are interested in eigenvalues is from this quadratic eigenvalues here are written in this compact form, because otherwise if you're extending them, as you can see, this is lambda square involved this. So within these techniques now, you literally, you can solve this eigenvalue province and using this quadratic eigensolver. So this is the sum of the picture to show you, how you can doing this. I think that the key is points here. So those are the number of the pixels or dimensional size, like in this graph or this daisy pictures. So they are all the dimension at hundreds of thousands or at even up to millions. So now using this quadratic eigensolver, we can get such a kind of clustering or solve such kind of optimization, Rayleigh quotient optimization, only in a matter of less than 2 minutes. Okay, so this is only take 21 seconds, and this is take about less than 100 seconds. So really demonstrated the efficiency of that. So this is the last of this work is in this papers. It's first appeared on the archive, but now it's going to be published soon. So in conclusion, so basically, I think the conclusion is very straightforward. So this type of Rayleigh quotient or Rayleigh type of objective quotient optimization or province are very common, as many of you already have seen. So since I'm more is working in the linear algebra, numerical linear algebra fields, so I'm more looking at underlying of the linear algebra structure and try to review them. So as you can see, you can encounter linear eigenvalue province, which is typically we have already seen, but you can also have some nonlinear eigenvalue province, like last one, the quadratic eigenvalue province you see. But of course, also include this type of nonlinear eigenvalue problems now involve nonlinear eigenvector. So it's really opened a tremendous opportunity to people like me and the students, and also build the bridge between people working optimization and also in the linear algebra. So that's all my talk. Thanks. Thank you.
Well, thanks, Professor Bai, for this beautiful talk. There's plenty of opportunity now for questions, so please feel free to post questions in the chat or just unmute yourselves.
Very nice and very interesting. So if you have eigenvalue problem, when do you transform to optimization problem? Do you have any principle?
There is a right now, as I say, I think this bilinear form are very essential. We are not afraid of some of such bilinear form, but so there is I don't know whether is that there is no general principle. First, I should say, but we know certain type of extension can be made. For example, the trace. If you only trace ratio, if you have a multiple sum of that trace ratio, we can also do type of things like that.
If a matrix is million by million, so when you do optimization, you don't need to access to the whole matrix?
No. So all this, like this techniques, we're going to all involve, and the line of them is doing a matrix vector multiply for all the eigensolver.
Right, but so you just assume you can do matrix vector?
Yeah, everything.
Okay.
This is the most fundamental assumption throughout the entire talk. Any matrices here, etc. But of course, for matrices, if you have clear Laplacian structure, etc. So when they do like a quotient format, the bilinear form, so you even has a more nicely expression, only nearest, connected edge you need to calculate, etc. So there's another sort of things under the hood you can explore.
How do your Rayleigh quotient ideas compare with other methods that also rely only on using matrix vector products? Like there are many ways of getting eigenvalues that require only doing matrix vector products, as you know. Yeah. When are these better?
I wasn't quite sure your question. You say.
So let me try again. There are other ways of calculating eigenvalues that work by means of computing matrix vector products. Right? Rayleigh quotient is only one way. There are other ways to calculate eigenvalues. How does your Rayleigh quotient approach compare to those other ways? When is yours better?
That's a good question. We did not really do quite an extended comparison yet. The reason is that in our, as you clearly see, many of those efforts still stayed on in terms of how to build such bridges. So our point at this, or entirely my talk, is try to this big diagrams here. So once you see this, how you find a connection with the eigenvalue. But in terms of this itself, certainly, I think it's a good research issues. I cannot give you the answer right away, which one is better. Certainly, thanks for the question.
But isn't one argument that your approach is basically amenable for optimization?
Yeah, that's certainly.
And the other methods for computing eigenvalues. I mean, I'm not saying they're better or worse. I'm just saying that if you want to use the machinery of nonlinear optimization, that's one way how you can do it, I suppose.
Yeah, in fact, I can do for that regard. For example, Rayleigh quotient types essentially is a fractional programming, nonlinear fractional programming. So we are using some simple type of nonlinear fractional method, like you probably know this Dinkenbach, etc. Back then, it's already can translate a certain rational, fractional nonlinear programming problems and into sort of roots finding of that. Then you can use Newton types of that. So we are in the process to compare within this type of approach. But our earlier approach, particularly because of this type of eigenvalue problems, or the optimization problems, people are naturally connecting within a so-called optimization on certain trace on the manifold. So therefore, this manifold optimization has been quite popular. They even has this package called ManOps. So we are using two of that. Certainly, we're realizing this might not be the right tool to comparison. To compare. Okay.
Yeah. More questions?
A specific question. Could we look at page 29 of the slides?
Okay.
For the relaxation.
Yeah, this is the relaxation.
Relaxation. So why don't we put a inequality there? Probably it's difficult to solve, I guess. For y.
So why the original problem is a bilinear optimization.
Right.
They only take a y as a negative or positive. But now we're just relaxing to entirely. It's really very easy to solve because this will turn into you might call it standard eigenvalue problems.
We could relax y to a box constraint, right?
Yes, that's
difficult.
That's probably, but then whether the difficulty level, etc.
Mm-hmm.
Because as you can see, amazingly for a picture like this, those eigenvector has a very, tell you a lot about the underlying of features. So more general picture like this, I went too faster. So all these are the eigenvector, the first, non-zero eigenvectors. So as you can see from those eigenvector, it's already reveals a lot what's about the underlying of that structure.
So the relaxation doesn't cause any problem.
Yeah, it's really just the whole point of simple. But of course, afterwards, how you use eigenvector to do the clustering on if the picture or underlying structure is complicated, the result will not be that as nice as this.
More questions?
Another question. For the equation h of v times v equals v lambda.
Which one?
You have the equation h of v times v equals v lambda.
This is a nonlinear. Yeah. This is in fact, this is a very. If you're looking at my paper, couple paper we posted, it's all about this eigenvalue problem because this is this type of that is right.
Right. So here, eventually, what kind of eigenvalue do you get? The smallest, largest, or?
No, it's if you're looking at this, so this lambda here, it must be the eigenvalues of these matrices. So now you are corresponding to, for different setting, this eigenvalue is different. But in this particular choice ratio, which is in fact turned out to be the simplest model now, we're realizing, it's just corresponding to the largest eigenvalues of that. So for some more complicated models, so if you're looking at my publication for this ones, if you're interested, sorry, I'm jumping around. So this is on the CISC, we published of a couple of years ago on the robust RQ. So we also has underlying nonlinear eigenvalue problem associated within them. But in this case, it's not the smallest eigenvalues.
Thank you.
Yeah.
Hey, I think it's a good point in time to wrap up and thank the speaker again.